All right, so tonight we're going to have a video on motion and especially motion graphs. We're going to be focusing on two ideas, velocity and acceleration. This video is going to be really detailed and we're going to focus on some really important subjects. I'm going to try to highlight those and make them as clear as possible. It's totally doable. If you can find slope, then you can do everything in this video. But I will warn you that it can be very difficult for students to keep all of this information in mind. That's why I'm doing this as a video, so that you can stop it, rewatch it, and you can watch it multiple times even. Some of you might find that you watch it 3 or 4 times before you take your test, and maybe even come back to it as a reference. So please watch it carefully. Please take some nice Cornell-style notes, leave space for questions and a summary. And make sure that those are pretty complete and detailed, especially highlighting the main ideas of what we're talking about. You don't have to do your questions and your summary until we do them in class. Now, at the top of this screen, I have some things that I want you to pay attention to. And one of them is the definition for velocity, which we already know. We already have written down a couple times that velocity is distance traveled in a certain amount of time. Velocity is a ratio between distance and time, and that's why we usually write velocity in the form of meters per second. Okay? Now, as we can see, we have a data chart right over here, and that data chart represents data from the car lab. So we had our little yellow cars, and we were driving them along, marking where they were each second. We can use that data to find velocity. So just to run over the data real quick, we've got 5 seconds marked, and we've got the position for each one. If I'm going to graph that, I'm always going to graph the position, or the distance traveled, sometimes we call it, on the y-axis, and the unit is going to be meters. And then I'm going to mark the time on the x-axis, and the unit is going to be seconds. Sorry, I need to dot my I's there. Goodness. And we're going to go ahead and plot those points. So at 1 second, the object's position is 5 meters. And we'll just put a little dot there. 2 seconds, the object's position is 10 meters. And 3 seconds, the object's position is 15 meters. And what we're going to get is a nice straight line on our data. And we can go ahead and draw that right there. So the importance of this is we want to know how to find velocity. Remember, that's what this whole thing is about. And as we've talked about in our car lab and also in subsequent activities, we should already know that to find the velocity of this graph, we're going to solve for the slope. So please understand that when we look at a position and time graph, the slope of this graph is velocity. I'm just going to write VEL because it saves me a little bit of time. Now, if you're writing that down in your notes, which you should be, I want you to make extra point of that, put a star next to it or something. But I also want you to mention that slope is velocity only for a position versus time graph. Make sure you write that down because slope is not velocity for everything, and that's a mistake that a lot of students end up making pretty frequently. So if we go ahead and look at this, if we do the rise over the run on this graph, we'll find that the rise is 5 meters for every 1 second. And so our slope is a velocity of 5 meters per second. Now you guys should already know how to do that. You should already know that if you look at a position and time graph, you can find the slope to find the velocity. And that's because velocity is change in position or distance traveled divided by time. Now, we're going to get to the new stuff. So the new stuff is talking about acceleration. And today in class, we did 2 kinds of graphs. We did position versus time graphs, and we also did velocity versus time graphs. Your little motion detectors, little devices that click and emit sound to measure range, they gave you one graph on the top, which was position and time. And they gave you another graph, which was velocity and time. And so I want to show you how those graphs are created, and I want to give you some rules for how those look and talk about how we use them to find acceleration. So that's a lot of stuff. Let's get into it. All right, so we just found the slope of this graph. And I want to point out that the slope of this graph is constant. And so no matter what points we were to pick, we would get the same number. We would get this 5 meters per second no matter what, because this is constant velocity. And so if I were to take this, I could make a new data table. And that's exactly what I'm going to do right now. So I'm going to make a data table over here of velocity versus time. And that velocity is going to be represented in meters per second. So notice the data I'm collecting from over here is now being transformed into velocity versus time. So I'm going to be graphing the slope of this graph into this data table. Okay? And let's go ahead and just write down those numbers. So the velocity for the first second is the slope. The slope was 5 meters per second at that time. It was also 5 meters per second at 2 seconds. It was also 5 meters per second at 3 seconds, 4 seconds, and 5 seconds, because like we said, the slope is constant, and therefore the velocity is constant. Okay, so this is constant velocity. It's the same number all the time. Now, I'm going to take that data from this data chart and I'm going to graph it down here. And I'm going to do a graph of velocity, VEL, in meters per second, and time on the x-axis in seconds. And we're going to do it exactly the same. I'm only going to write a couple points just to save some time. So the first second, so second 1, second 2, second 3, I was going 5 meters per second the whole time. So my first point's right here, the second point's right there, the third point's right there. So this is going to give me a straight line that is also horizontal. Okay, so just to recap, this is a graph of position and time. The object goes the same distance each second, and so we get this nice slope that goes up. This is the exact same data, but we're graphing velocity and time this time. And since so this is what constant velocity looks like when we're tracking position and time. This is what constant velocity looks like when we're tracking velocity and time. If you go back to your notebook and you look at, just checking what page it is, if you look at page 26 of your notebook, this is what we did in class. Your motion detector created graphs of position and time and velocity and time and matched them together. Okay? Now, the next step, we're going to be talking about this new idea of acceleration. So acceleration is the change in velocity in an amount of time. So it's also a ratio. But it's not a ratio of meters and seconds like velocity was. It is a ratio of velocity per second. And so when we write out acceleration as a ratio, it is the unit of velocity. Notice the unit of velocity is meters per second. We're going to take that, we're going to bring it all the way over here, and we're going to do meters per second is so that's the unit of velocity, but we're looking for the change in velocity each second. So it has to be a unit of meters per second, because acceleration is change in velocity, which is measured in meters per second, divided by the amount of time it takes. So it's meters per second. We also write that as meters per second squared. Okay, so that can also be the unit of acceleration. Now I'm going to look at this velocity versus time graph to find the acceleration, because we just said acceleration is a ratio of velocity and time. So to find it, we're going to find the slope of this graph. The slope of a velocity and time graph is not velocity, because velocity is the y-axis. The slope is acceleration. Okay, so this slope is acceleration. Now if we look at this line, we can see that the slope is 0. It's not going up, it's not going down, it's horizontal. And so the acceleration in this case would be 0 meters per second squared. We are not gaining any velocity, we're not losing any velocity, it is constant velocity. So we write that as 0 meters per second squared. Okay, so we just reset my screen real quick to show you a different example. And I want us to look at a new example of position and time. Our last one was something we should have been familiar with, which is constant velocity. The object was going the same distance each second. And so the velocity was the same the whole time. You had a nice horizontal line on the velocity graph. And we found the acceleration to be 0 meters per second each second, because the object was not accelerating, it was not speeding up or slowing down. This one is going to be accelerating, so the velocity is going to be changing. So I want us to look at the effects of that. So I've got the position over here, I've got the time over here. I'm going to go ahead and graph that on a position versus time graph. Remember, this is position, we're measuring that in meters. Okay, this is time, and we're measuring that in seconds. Okay, we're going to have 1 second, 2 seconds, 3 seconds, and I'm going to draw the whole thing here, 4 seconds and 5 seconds. And so at the beginning, my object is only gone, it starts off at 0, and after 1 second, it has only gone 2 meters, so not very far. After 2 seconds, it has gone 6 meters, which is farther. After 3 seconds, it has gone 12 meters. After 4 seconds, it has gone 20 meters. After 5 seconds, it has gone 30 meters. Okay? Now, I actually should notice at this point, it's a little hard to see, but this is actually not a straight line. It doesn't have constant slope. It goes up by 2 meters in the first second, and then up by 4 meters in the next second, and so on and so forth. So this is actually a curve. I'm going to do my best to draw this. To draw a curve on here, it's kind of hard. I'm just going to do a bunch of lines. So like this line, and then that line, and then that line, and that one, and then that one. So you can see that that's a little bit curved. So the first thing I want you to know is that when an object accelerates, the position versus time graph will be a curve. Ooh, what happened there? Sorry, I had a little bit of a freak out on my pen right there, but the position versus time graph will be a curve. I want you to specify, if you're writing that down in your notes, make sure you know that it's not every graph will be a curve when you accelerate. It's only the position. And that's because you don't go the same position, the same distance each second when you're accelerating. You go a little bit, You go a short distance and then a longer distance and a longer distance. Still, we can find the velocity by looking at the slope. But the problem with a curve is it has many slopes. And if you're familiar with some advanced mathematics, like calculus for whatever reason, there's a lot of tools and techniques to find slope that are really, really accurate. But for this level of physics, we're just going to find the slope over each individual second. Okay, it's not going to be quite as accurate as some of these other techniques that we might use, but that's how we're going to do it. Okay, so let's go ahead and find the slope for each part. So this first part goes up 2 meters and over 1 second. So that's a velocity of 2 meters per second. And we're going to write that into this chart over here. Use a different color actually. So we're going to go up and over. We're going to write that into the chart here. It's going to be velocity in meters per second. And I'm just going to write that as the velocity for the first second. Now, technically, it's actually the velocity for the time between 0 seconds and 1 second. It's actually the velocity, the average velocity over that time. So you'd really want to put it somewhere in between. Again, that's a little more detail than I'm worried about at this point. So just for this graph, we're going to go ahead and write that velocity, it went 2 meters in 1 second. So we'll just write 2 meters per second right there. And then for this part, it actually goes from 2 to 6. So see this jump right here, 2 to 6? That is 4 meters in 1 second. So we're going to write 4 meters per second here. This next jump is from 6 up to 12. So that's a jump of 6 meters in 1 second. Notice the velocity is increasing. Now our slope, we go from 12 to 20. That's a jump of 8 meters in 1 second. So our velocity is 8 meters per second. And then lastly, we've got a big jump of 20 to 30. So that's a jump of 10 meters in 1 second. Okay, so we're going to go ahead and plot that onto our velocity graph. And again, this is velocity in meters per second. I just want to make sure that I, write my units every time. And this is time in seconds down here. And when I go ahead and graph this, I'm going to have time for the first second, I'm going to have time for the second second, I'm going to have time for the third second, and I'm going to plot these points in here. So this is going to be 2, this is going to be 4, I'm not going to draw every single point because it's going to take too long, and this is going to be 6. And so what we're going to see pretty quickly is that the velocity is now increasing, and we actually get a approximately a straight line going up like this. Okay, so that's huge. Notice, when we are accelerating, the position versus time graph is a curve, but the velocity versus time graph, which before was a straight line, is now a straight line that slopes upward. And we can actually solve for the slope. We already said that the slope of this line is acceleration. Hold on a second. I want you to go ahead and make sure that you added that to your notes. Make sure that you add that for an accelerating object, the velocity versus time graph will be a straight line that slopes up or down if it was decelerating. But this one is going up. And then also remember that we can find the acceleration of this object. I want to mention that acceleration is the slope of the velocity versus time graph. Okay, so I'm going to go ahead and solve for the slope of this graph. It goes up 2 meters per second in 1 second, up 2 meters per second in 1 second, up 2 meters per second in 1 second. It's pretty consistent. So always the rise is 2 meters per second of velocity over 1 second. So if we actually do the math on that slope, I want you to, the math is easy, obviously, but I want you to look at the units. It's 2 meters per second over 1 second. Okay, so do you see why the units will end up being so weird for acceleration? It's 2 meters per second squared. Okay, which means that every second you're gaining 2 units of velocity. Okay, your velocity goes from 0 to 2 to 4 to 6 to 8 to 10. Okay, so this is where everything gets kind of complicated. Okay, we need to keep track of the fact that slope of a position graph is different from slope of a velocity graph. The slope of a position graph shows you the velocity. The slope of a velocity graph shows you the acceleration. You have a bunch of examples of this in your notebook already from the motion detector lab. You might want to look back over those now knowing what you're looking for. And we're also going to do a bunch more examples in class. But those are the big ideas I want you to take away. If you can remember what the slope of a position graph means and what the slope of a velocity graph means, you're going to do just fine. All right. Well, thank you so much. I know this video was a little bit long, but there's a lot to talk about here. I hope you took some solid notes. Remember, you don't have to do questions or a summary until we see each other in class tomorrow. Can't wait. Thanks. Bye.